Hello friends, we are going to start a series on structural geology, of which this is the first episode. Structural geology is one of the most important branches of geology. To comprehend the subject of geology as a whole, it is essential to learn about structural geology. Structural geology, as you know, helps us in understanding the evolution of the rocks in an area, especially on the continents where very old rocks, about 4 billion years old, are preserved. The interpretation and analysis of the structures in the rocks helps us in understanding the process of evolution of rocks through this large geological time. Structural geology is also essential to apply and extract economic mineral resources like metallic ores, like hydrocarbons, both oil, coal and gas. So, let us start with what structural geology is all about. Structural geology analyzes and interprets the structures of the different types of rocks, igneous, sedimentary and metamorphic, as found on the Earth's surface. The structure of a rock is defined by the various structural elements, which are both planar and linear in nature. Planar structural elements, for example, the colored layers in a sedimentary sequence that are made up of different materials or different composition, or the banding or rock cleavage, the close spaced planes in a metamorphic rock, along which the rock has a tendency to split into slabs like slate. Linear structures include the linear arrangement of mineral grains that has one dimension much greater than the other two, which is governed by the forces applied on the rock either at the time of formation or subsequently during deformation. So, first of all, let us discuss the different types of structural elements that are found in rocks. In igneous and sedimentary rocks, certain planar and linear structures form when the rock is either cooling down, crystallizing from a molten magma or lava, or during the time of deposition or immediately after deposition, before the loose sediments are consolidated into sedimentary rocks. These structures, the planar and linear structural elements that form in a rock at the time of their formation or immediately after, without application of any directed stress or diastrophic forces, are called primary or non-diastrophic structures. In metamorphic rocks, on the other hand, during their deformation, several planar and linear structures may develop in response to the directed stress. They are known as secondary or diastrophic structures. Primary structures, the most important structure in a sedimentary rock is bedding, which is defined by different layers of different color, composition and grain size, and usually marked as planes of various width within a sedimentary sequence. After deformation, these layers, which are usually deposited horizontally, are deformed into various shapes and give rise to deformation structures known as cleavage or foliation. In igneous rocks, the early formed minerals, which are flaky in nature like mica, they orient themselves parallel to one another and usually parallel to the boundary of an intrusive igneous rock and perpendicular to the movement direction. Similarly, linear minerals like amphiboles, they orient themselves parallel to the direction of flow in a lava, thus giving rise to a linear structure. Now, about secondary structures or deformation structures. Secondary or deformation structures are produced in a rock when it is undergoing metamorphism under a directed stress. In response to the directed stress, platy minerals or elongated needle-like or linear minerals orient themselves to the position of most stability, thus imparting a secondary planar or linear structure to the rock. Of the primary and secondary structures, there are two basic kinds. Most of the secondary structures that develop, they can be observed at all possible scales, from grain scale to regional scale running for miles. These structures are known as penetrative structures, structures that can be observed at all possible scales, while those structures that are seen only on a large scale are known as non-penetrative structures. Now, next we move on to how do we measure or describe the orientation of a planar or linear structure. For our convenience, scientists have devised certain parameters to describe the orientation in space of planar and linear structures. Of a planar structure, it is important to convey the orientation of a planar or linear structure to a person who may not be actually viewing the structure in the field. So, it is essential to describe the orientation in space completely. For the purpose of description, we have been using certain parameters, of which the most important parameter for a planar structure is strike. If we look at a planar structure inclined at a certain amount to the horizontal, there is a plane ABDC. Strike of the plane ABDC is defined as the azimuthal direction or geographical direction of the horizontal line on that plane. The line AB is a horizontal line on the plane ABDC, which may be interpreted as the line of intersection between a horizontal plane and the inclined plane. The horizontal line on any inclined plane is called the strike line. There are infinite number of strike lines possible on a plane, but all of these lines will have a single geographical direction. The geographical direction of the strike line of an inclined plane is known as the strike of that inclined plane. The next step in defining the orientation in space of a plane is its inclination. The inclination of a plane with the horizontal is referred to as its dip. If we look at the plane ABDC, we can see that this plane is making an angle theta with the horizontal when viewed on a vertical plane that runs perpendicular to AB or the strike of the plane. So, the angle theta is known as the dip amount, while the direction of dip is defined as the horizontal direction perpendicular to the strike AB. So, if we convey to a person the strike of a plane, its dip amount and dip direction, the orientation of a plane is defined completely. We must understand that a plane has different inclinations along different directions. Let us put it this way, that if we are standing at the base of a uniform hill slope and we are trying to climb up to the top of the slope, we may move in different directions. The direction perpendicular to the strike of the slope is the shortest line of ascent, but has the maximum slope. But if we move in a different direction other than the line normal to the strike, we will have to travel a longer distance, but will climb a much gentler slope. This is the line of shortest ascent, but the steepest, while if we move along this direction, we will have to travel a much longer distance, but a much gentler gradient. So, a plane similarly has inclinations of different amounts in different directions. The maximum inclination of a plane with the horizontal is known as its true dip, while the inclination measured in any other direction is known as its apparent dip. So, it is understood that the apparent dip of a plane in any direction cannot exceed the amount of true dip. Next, we move on to the measurement of orientation of a line. Orientation of a line or a linear structure in a rock is defined by the parameters plunge and pitch or rake. Let us try to understand the complete definition of plunge of a line. When a line is inclined to the horizontal, its orientation can be described in terms of its inclination with the horizontal plane and its trend or the direction in which it is inclined. If we imagine a line lying within this block, the line AB, the diagonal within the box, it is lying on two planes actually, one ACBD, which is a vertical plane, and it may also be imagined to lie AEBF, which is an inclined plane. Plunge of a line is defined as its inclination with the horizontal, which is measured on a vertical plane, which is imaginary, maybe an imaginary vertical plane that contains that line. In this case, the angle CAB or theta is the amount of plunge, while the directional vector AC, the direction in which the line is inclined, is known as the direction or trend of plunge. On the other hand, the angle that the inclined line makes with the horizontal line on an inclined plane, like on the plane AEBF, the angle BAE, the angle that the inclined line AB makes with the strike AE of the inclined plane, is known as the pitch or rake of the direction of pitch or rake is something to be understood clearly. Conventionally, we always measure the acute angle, because you can see that on an inclined plane, if there is an inclined line, it makes two angles with the horizontal line. One is acute and the other obtuse. Conventionally, we always measure the acute angle as the amount of pitch or rake, and we represent the direction of pitch or rake by mentioning the horizontal direction with which the acute angle is made. In this case, the acute angle is made with the direction AE. So, we state the direction of pitch as phi degrees from E, from the E end of the strike line. There is a corollary to this. If we go back a little to the sense of apparent dip, the angle between an inclined plane and the horizontal measured in a direction other than perpendicular to the strike, the angle is measured on an imaginary vertical plane in that direction. So, the angle between the line of intersection of the plane and the horizontal line on that vertical plane is the amount of apparent dip, and so is the plunge. So, if we have a line lying on an inclined plane, the plunge of the line and the apparent dip of the plane in that direction will be identical. So, this is a lesson for the beginners in structural geology, that when we go to the field, measure the orientation of structural elements, we must keep in mind that no line on a plane can have a greater amount of inclination than the true dip of a plane, the same way that the apparent dip of a plane cannot exceed the true dip. There is another corollary to this. The plunge of a line is measured on a vertical plane and the pitch on a inclined plane, both with the horizontal. Thus, if the line happens to lie on a physically existing vertical plane, then the plunge of the line and pitch of the line on that plane is identical. The difference between plunge and pitch of a line is this, that plunge of a line can be defined independent of any plane. Just by stating the amount and direction of plunge, we can completely describe the orientation of a line, but to define the orientation of a line with the help of the parameter pitch, it is important to also describe the complete orientation, the strike, dip, true dip amount and true dip direction of the plane on which it lies. The dip direction of a plane may be defined as the direction in which we encounter successively lower points on an inclined plane. If we represent it this way, the line of true dip AB on the inclined plane is projected vertically onto the horizontal surface to the line AB dashed. If we proceed from A towards B dashed, we encounter points which occupy successively lower heights on the plane. Thus, the dip direction is the direction in space in which we get successively lower points. Similarly, the plunge direction can also be defined in similar manner. The direction in which, if we move along the vertical projection of an inclined line on the horizontal surface, we encounter successively lower points on the line. The analysis and interpretation of the structure in a rock depends on the complete measurement of the orientation of different planar and structural elements present in the rock, because the orientation of the different structural elements, planar and linear, especially in a deformed rock, gives us an idea about the deforming forces, the direction from which the stresses responsible for the deformation came, and it also helps us in understanding the large scale tectonic movements of the Earth's superficial fragments known as the lithospheric plates. Well, that concludes our first episode defining the scope of structural geology, the importance of structural geology, and the ways and means of analyzing and interpreting the structures in a rock. We have seen how the structure of a rock is defined by the planar and linear structural elements present in it. We have seen how the orientation of planar and linear structural elements are measured and represented, conveyed to a person who is not actually viewing the structures in the field. We have observed how the variation in inclination of a plane is defined by defined parameters. We have seen how the orientation or inclination of a plane and the inclination of a line lying on that plane is related to each other. That is, we have known what is the strike of a plane, the true dip of a plane, the apparent dip of a plane, and the plunge of a line lying on the same plane. We have also seen how the term pitch or rake is defined in respect to an inclined plane, and how the pitch or rake of a plane, the pitch or rake of a line and the plunge of a line is related if the line lies on a vertical plane. So, at the end of this episode, we will speak briefly about the next episode that we are going to take up. Our next episode will be on unconformity. Unconformity is a break in the geological record of an area as found especially on continents. An unconformity, as the name implies, means a non-parallelism between two sets of rocks. We will be discussing about the various types of unconformities, how to recognize them, and their significance in structural geology in our next episode. Thank you.